Here's something that sounds like it should be true. If your computer is too slow, just add more power, more processors, more memory, more chips, until it can handle anything you throw at it. Tech companies have spent hundreds of billions of dollars chasing exactly that idea. But there is a problem nobody can engineer their way around. Past a certain point, adding hardware does almost nothing. You can double the processors and get 5% faster. The machine fights back. And the reason comes down to a few invisible walls that every computer on Earth runs into, including the one you're using right now. For about 40 years, the dream actually worked. Inside a silicon chip fabrication plant, engineers kept finding ways to shrink transistors, those microscopic switches etched onto a polished wafer of silicon. Smaller transistors meant you could fit twice as many in the same space roughly every 2 years. That observation even earned a name, Moore's Law, after the Intel co-founder who first spotted the pattern. And for a long time, twice the transistors really did mean a far faster machine. Computers got faster, cheaper, and smaller, all at the same time, year after year, like clockwork. A glowing processor on a green circuit board from 1995 would look laughably slow sitting next to one from 2005. This is the era that trained every one of us to believe that more is always better. If you wanted a faster machine, you simply waited a year, or you bought a bigger one. There was barely a reason to write leaner software, because next year's hardware would bail you out anyway. It felt less like a trend, and more like a law of nature, a guarantee baked into the universe. Here is just how good it was. For decades, the raw speed of a single processor improved somewhere between 30 and 50% every single year. Today, that figure has collapsed to around 3% a year. The engine that drove the entire digital revolution did not just slow down. It nearly stalled. And the strangest part is that it stalled even as we kept getting better at packing in transistors. The chips kept gaining parts. The speed stopped following. So what happened? Why did adding more quietly stop working? To answer that, you have to meet the walls one at a time, because each one is a completely different kind of barrier, built from a completely different piece of reality. And the moment you try to stack your way to infinity, you crash straight into all 5 of them. The first wall showed up decades before anyone hit it. In 1967, a computer engineer named Gene Amdahl stood up at a computing conference and pointed out something that should have ended the just add more dream right there. His argument is simple enough to feel at a dinner table. Imagine you are cooking a huge meal and you hire more and more chefs to speed things up. Chopping vegetables splits beautifully across many hands. 10 chefs chop roughly 10 times faster, but some parts of the job just cannot be divided. Someone still has to decide the menu. The oven still bakes the bread for the same 40 minutes, whether you have 1 chef or 100. Those steps are stuck. They happen in order, one after another, no matter how much help arrives. Amdahl put a number on it, and the number is brutal. Every computing task has a part that can be split across processors, and a part that simply cannot. Say you are lucky, and 95% of your job can be parallelized. You might think 1,000 processors gets you close to 1,000 times faster. It does not. The 5% that stays stuck in line becomes the bottleneck, and the absolute best you can ever do is about 20 times faster. Not 1,000. 20. And here is the part that breaks people's brains. It does not matter if you add 1,000,000 processors or 1,000,000,000. That ceiling does not move. The serial slice of the work sets a hard limit, and no amount of hardware on the planet can push past it. You can watch this happen in something as ordinary as rendering a video. Exporting a film splits gorgeously across many cores, since every frame can be processed at the same time. But the final step, stitching those frames into one ordered file and writing it to the drive, has to happen in sequence. Throw 100 cores at the job, and that last serial stretch barely budges. The render gets faster, then hits a wall, and the wall is made of the one part you could not divide. Now, to be fair, there's a famous counter-argument here, and it matters. A computer scientist named John Gustafson pointed out that in the real world, when people get more processors, they do not run the same small job faster. They run a much bigger job. Weather models get more detailed, game worlds get larger, simulations get finer, and bigger problems tend to have a bigger parallel slice, which softens Amdahl's ceiling, so the limit is not quite as airtight as it first sounds. But notice what that argument quietly admits. You're not making a fixed task infinitely fast. You are just choosing to solve a bigger task in the same amount of time. The wall is still there. You have simply agreed to stop pushing against it. So the dream of infinite speed dies on the very first wall. But let us be generous and pretend you found a problem that splits almost perfectly. You are still not safe, because the second wall is waiting, and it is the cost of teamwork itself. Processors that work together have to talk to each other. They share results, they wait for each other, they agree on what is finished and what comes next. And the trouble is that this conversation gets more expensive shockingly fast. Picture a cluster of processors on a server board, each one needing to stay in sync with the others. With 4 chips, there are 6 possible connections between them. With 8 chips, there are 28. With 16, there are 120 separate lines of communication to manage. The coordination grows far faster than the number of workers. You have felt this exact problem in real life. A project with 2 people is fast because the 2 of you just talk. Now run that same project with 50 people. Suddenly half the day is meetings, status updates, and waiting on someone else before you can move. At some point, adding another person to the team actually slows everything down because the cost of keeping everyone aligned swallows the work they came to do. Processors hit the same wall, add enough of them, and they spend more time managing the conversation than actually computing. And there is a second, sneakier cost on top of that. Processors working together constantly have to stop and wait for each other to reach the same checkpoint before they continue. Engineers call this synchronization, and it means the whole group can only move as fast as its slowest member. Imagine 100 runners who have to link arms and cross every line together. One slow runner, and all 100 crawl. It does not matter that the other 99 are fast. The group is hostage to the weakest link, and the more processors you add, the more likely it is that at any given moment, one of them is the straggler holding everyone up. There's a point where the next chip you bolt on makes the whole machine slower, not faster. That is not a bug in the design. That is the mathematics of coordination, and you cannot buy your way out of it. Now suppose you somehow tame the teamwork problem too. There is still a third wall, and this one is about a quiet kind of starvation. A processor is only useful if it has something to chew on. It needs a constant stream of data and instructions pulled in from memory. And for decades, the speed of the processor and the speed of the memory feeding it have been drifting apart at a frightening rate. Researchers gave this a name back in 1994. They called it the memory wall. The numbers behind it tell the whole story. Processor speed was climbing by roughly 60% every year. The speed of pulling data out of main memory was improving by only about 7% a year. When one thing races ahead and the other crawls, the gap between them does not just grow, it explodes. Today, a modern processor can run hundreds of operations in the time it takes to fetch a single value from main memory across the circuit board. So your blazing fast chip spends a huge chunk of its life doing nothing, just sitting there idle, waiting for the next piece of data to arrive, like a chef standing at an empty counter waiting for ingredients. Engineers fought back with clever tricks, mostly small pools of ultra-fast cache memory sitting right next to the processor core, holding the data it is most likely to need next. Modern chips stack these in layers, a tiny, lightning-fast cache closest to the core, a slightly larger and slower one behind it, then a bigger one behind that, each level a compromise between speed and size. And it helps enormously. But it is a patch, not a cure. The fundamental problem remains. You can make the processor as fast as you want, and it will still spend most of its time hungry, because the pipe feeding it is both too narrow and too long. It gets worse when you look at energy. On a modern chip, the act of moving a piece of data from memory over to the processor can burn far more energy than the actual calculation that data is used for. Read that again. Fetching the number costs more than crunching it. So the bottleneck is not just about time anymore. It is about heat and electricity too, which is a problem that comes back to haunt us in a moment. Stacking more processors onto this just creates more hungry mouths, fighting over the same crowded pipe to memory, each one demanding to be fed, most of them left waiting. If you're getting value out of this, take 1 second to subscribe. I break down the hidden engineering behind everyday technology every single week, and the next one builds directly on what we are about to cover. Now let us get to the wall that actually rewrote the history of computers. Let us say you decide to ignore every limit so far and just go brute force. Cram in more transistors, switch them faster, push the clock speed higher and higher. This is where the fourth wall stops you cold, and its weapon is heat. Back in 1974, an engineer named Robert Dennard described a beautiful rule. As you shrink transistors, you can also lower their voltage, so the power packed into each square millimeter of chip stays roughly constant. In plain terms, smaller transistors meant you could run them faster without the chip getting hotter. This rule, called Dennard scaling, is the secret engine that powered those 40 golden years. Faster and cooler at the same time, generation after generation. Then, somewhere around 2005 to 2007, it broke. The physics simply gave out. Below a certain size, you can no longer keep lowering the voltage, because the transistors start leaking electricity even when they are supposed to be off, like a faucet that will not fully close. That leakage turns straight into waste heat. Push the clock speed higher now, and the chip does not just warm up, it threatens to cook itself. You can actually see the exact moment the industry hit this wall. In 2004, Intel quietly canceled a planned 4 GHz processor because cooling it had become a nightmare. And here is the wild part. 20 years later, the clock speed of a typical processor is still sitting right around 3 to 4 GHz. That number basically froze in place 2 decades ago. This is the real reason your laptop has multiple cores instead of one impossibly fast one. The industry hit this cliff around 2005 and made a hard turn. Unable to make a single core meaningfully faster, chipmakers started placing several slower cores side by side on the same piece of silicon and hoping software could split the work between them, which, as you now know from the very first wall, only works for the parts of a program that actually divide. The free ride was over. For the first time in decades, faster hardware stopped being automatic, and the burden quietly shifted onto programmers to write code that could use all those cores at once. But even the multi-core trick runs into a ceiling, and engineers gave it a haunting name. They call it dark silicon. On a modern chip, there's so many transistors packed so tightly that you physically cannot power all of them at full speed at the same time without melting the thing. So large regions of the chip have to sit dark, switched off, waiting their turn, just to keep the temperature survivable. You paid for those transistors. You literally cannot use them all at once. This is also why your phone slows itself down when it gets warm in your hand. The hardware is right there, fully capable. The heat simply will not allow it to run. Stacking more silicon does not escape this. It just gives you more transistors you're forced to leave in the dark. So the dream is bleaking heat, choking on coordination, starving for memory, and crashing into Amdahl's ceiling. And now we arrive at the final wall, the one that makes all the others look negotiable. Because this last barrier was not made by any company, and no future breakthrough will ever remove it. In the late 1960s, a Navy officer and computer scientist named Grace Hopper started doing something strange in her lectures. She would hand every person in the audience a short piece of wire almost exactly 1 foot long. Hold on to it, she would tell them. That little piece of copper, about 30 centimeters, is the farthest electricity can travel in 1 nanosecond. 1 billionth of a second. She was making something invisible suddenly fit in your palm, and her point cut to the bone of the entire problem. The speed of a signal inside a computer is not really limited by money, or cleverness, or how many chips you can afford. It is limited by the speed of light. Think about what that means for a giant machine. Every time a signal has to cross from one side of a processor to the other, or from one server rack to another across a data center floor, it takes real time, and that time can never be less than the distance divided by the speed of light. So the bigger you build your machine, the farther every signal has to travel, and the longer every step takes. Scaling up does not just hit diminishing returns. It actively works against you because size and speed are now pulling in opposite directions. Let me make that concrete. A processor running at 3 gigahertz ticks 3 billion times every second. In the sliver of time between two of those ticks, light in a vacuum travels less than 4 inches. Less than the length of your hand. That is the entire distance a signal can possibly cover before the processor needs the next answer. Build your chip any larger than that, and parts of it literally cannot talk to each other fast enough to keep up. The size of the machine is now fighting the clock. Hopper had a second prop to drive it home, a coil of wire 984 feet long, to show the distance light covers in a single microsecond, 1,000 times slower. And later, when chips got fast enough to count in picoseconds, trillionths of a second, she switched to handing out grains of pepper, because that was now the distance electricity could travel. The lesson never changed. To go faster, you have to go smaller, not bigger. But going smaller has its own cliff. Shrink the components far enough and you slam into the bizarre rules of quantum physics, where electrons stop behaving like tiny little signals and start tunneling straight through barriers that are supposed to block them. The switch stops being a reliable switch. So you are squeezed from both ends. Too big, and the speed of light drags you down. Too small, and quantum weirdness breaks the hardware entirely. This is not an engineering challenge waiting for a smarter team with a bigger budget. It is a limit on causality itself, the maximum rate at which any signal, anywhere in the universe, can carry information from one point to another. No money moves it. No genius edits it. It is simply the final wall standing behind all the other walls. So if you cannot stack your way to infinity, what does the actual frontier of computing look like when humans push as hard as they possibly can? Go to Oak Ridge National Laboratory in Tennessee, and you will find it. In 2022, a machine called Frontier became the first supercomputer on Earth to break what is called the exascale barrier. That is a quintillion calculations every second, a 1 followed by 18 zeros. To get there, engineers did not simply pile up chips in a warehouse. Frontier is around 9,400 connected nodes, holding more than 37,000 graphics processors, woven together with about 90 miles of networking cable. It fills 74 towering cabinets, each one weighing roughly 8,000 pounds, and the whole thing has to be cooled by water pumped directly through the racks, because air alone cannot carry the heat away fast enough. It costs somewhere near $600 million to build. And here is the number that proves everything we just talked about. Frontier draws around 21 megawatts of electricity, roughly the power of 15,000 homes running constantly. Its predecessor, a slower machine called Summit, drew about 13. Now watch what happens when you look backward. Back in 2009, engineers tried to estimate what it would take to reach exascale using the technology of the day. Their answer was terrifying. Scaling up, the leading supercomputer of that era would have demanded something close to 3 gigawatts of power. That is the output of a large nuclear plant, feeding a single computer. So how did Frontier land at 21 megawatts instead of 3,000? Not by stacking more hardware. The opposite. Teams spent more than a decade attacking every wall in this video, finding ways to move less data, leak less heat, and waste fewer cycles waiting. The energy cost to do one exaflop of work dropped from roughly 330 megawatts in 2012 to 65 in 2018, to under 20 by the time Frontier arrived. Every generation got faster by getting smarter, not bigger. The fastest machine ever built is not a monument to stacking. It is a monument to how brutally hard you have to work, just to avoid being punished by these limits. Which leads to the real lesson hiding underneath all of this. The future of computing was never going to be a bigger pile. It was going to be a smarter one. In 2018, two of the most respected names in the field, John Hennessy and David Patterson, accepted computing's highest honor, the Turing Award, and used their lecture to declare something striking. They said the industry was entering a new golden age for computer architecture. Not because of more transistors, because of the opposite. Because the free ride was over, and engineers would finally have to design hardware and software together, shaped around the exact problem they were solving. You can already see it in the device in your pocket. Instead of one all-purpose chip trying to do everything, modern phones carry a whole team of specialized processors, each one built for a single kind of job. There is the main processor, a graphics chip tuned for visuals, and a separate dedicated chip built only for artificial intelligence tasks. Google built an entire processor called a TPU for nothing but the math behind machine learning, and it sips a fraction of the energy a general chip would burn doing the same work. Each one wins by doing one thing exceptionally well rather than everything poorly. They do not beat the walls by brute force, they tiptoe around them. And the deepest shift of all is in how engineers now think about data itself. For decades, the entire goal was to make the processor faster. Today, the smartest designs obsess over moving computation closer to where the data already lives, so signals barely have to travel at all. Remember, moving the data costs more than crunching it, so you stop moving it. As for quantum computers, the technology people love to call the savior, even Hennessy and Patterson have noted it is likely a decade or two away from being a practical replacement, and it solves a narrow class of problems, not your everyday machine. The real gains, the ones arriving right now, come from being clever, not from being colossal. That is the quiet revolution. The question stopped being, how many chips can we add? And became, how little can we move? Because every one of these walls, the serial bottleneck, the coordination tax, the starving memory, the heat, and the speed of light, every single one of them punishes movement and excess, and every one of them rewards restraint. The machine that wins is not the one with the most hardware. It is the one that wastes the least. So the next time someone tells you a problem will be solved by just throwing more computing power at it, you will know the truth. Somewhere down the line, that machine is going to hit a wall it cannot buy its way past. Maybe it is the math of Amdahl. Maybe it is the heat. Maybe it is light itself, refusing to go any faster. There's always a ceiling. The only real question is which wall you hit first. If this changed how you see the device in your hand, subscribe and stick around. On the screen, there's video where I will break down the strange engineering trick that lets a tiny chip in your phone do work that filled an entire room 50 years ago. It is the other half of the story, and you do not want to miss it.